Imperial College London. And so this talk is going to be a lot of arm waving and everything, so apologize for that. They're just basically ideas I'm trying to develop and implement these days as a side project. So just before starting, I'd like to acknowledge these people, especially Martin, that's my postdoc boss, and Natalie, that was my PhD supervisor. And yeah, so as a brief introduction, Graham actually kind of talked about that in the session just before. When we look at like a group of species like that, also, yeah, another disclaimer, I'm not working on dinosaurs, I'm not working on birds, but they make kind of cool silhouettes, so that's why I put them in the talk. Yeah, so if you have like these two groups or extended fossil species, basically we're interested in biodiversity and all this thematics and everything. You can see, for example, in these two groups, they have the same species diversity, so you count 9 species on each side and everything, but like from intuition, we want to say that basically the group of the birds has a higher morphological disparity than the group of theropods that kind of all look a bit the same, and yeah, you have more different shapes and functions maybe in the groups of birds. So yeah, like one of the big thing is how actually can you measure that and test if the group of birds here has a higher disparity, so a higher morphological disparity than the group of theropods there. So one thing you can do is you can basically just measure some traits on your species, for example the length of the legs, the length of the beak, and ordinate your species along these axes. So yeah, I'm just gonna show the example with these guys. Of course, there's more traits to these species than just tooth traits. So at the length of the wings, for example, and then you have basically you can represent your species in this kind of 3D morphospace. Again, you can order them like that. But of course, there's not only 3 traits in birds, so you can add a 4th one. But then that kind of breaks physics because there's 4-dimensional blobs. I cannot draw them. And of course, you can add more and more traits up to as many dimensions as you want. So one way to get all these traits is to use cladistic matrix. So basically, in this matrix, we have morphological traits that are represented by just discrete character states, and you can have basically these morphological matrices with, of course, you can have missing data, inapplicable data, etc. That's not such a big deal. And from these morphological matrices, you can use basically ordination to create this morphospace where these axes now, in comparison with the example I showed before, they don't mean exactly the length of the legs or whatever, but they're basically vectors of variance, of morphological variance in your matrix. And of course, there's more than 3 dimensions, etc. For doing that, actually, I advise you, if you guys want to do that, to use Graham's excellent Cladis package that's on R or on GitHub. So I'm not going to go expand on that. So I'm just going to go back on this example where I'm not using ordination, so I think it's a bit easier, but you can imagine these axes as just being your ordination axis. So again, back in our problem, we want to measure disparity. So for example here, we have our 2 traits, length of the beak, length of the legs, and we want to measure the disparity of the overall group. So there's many ways. So for example, here I've drawn an ellipse, but like you can measure the volume of this ellipse, or just the variance along the axis, like lots of people use like sum of variance, or the ranges along these axes. I think I'm going to talk a bit more about ways to measure that. There's many ways to measure it. But basically, we want to see the disparity of the overall group and the disparity of just these guys in blue. And we expect that the disparity, just from looking at this graph, that the disparity from these guys in blue will be smaller than the overall disparity. Now there's a problem here, because here we're just using only 2 dimensions. So if you add your 3rd dimension that we talked about, the length of the wings, well, already it's become a bit less unclear if, it becomes a bit more unclear, sorry, if the disparity of the overall group is actually bigger or significantly smaller than the disparity of the smaller group. And again, that goes up and up when you increase the number of dimensions. So basically there's a dimensionality problem here that when you look graphically just at 2 or 3 dimensions, you cannot solve this problem. So one way to measure that, again there are many other ways, but this is just one I kind of suggest, is again if you have your morphospace here and you have these 4 species, you can basically just calculate the centroid of this group, so that is basically the gravity point of this group, and just measure the Euclidean distance between the central point and each species. And that's actually really easy, useful, because Euclidean distances you can do in any number of dimensions. So basically that doesn't matter how many dimensions you are, you can basically just measure the distance between each of your species and the center of the morphospace. And basically you can have a distribution of the distances between each species and centroid of your morphospace. And that kind of measure could be used as a disparity, as a proxy of the size of the group, the volume, let's say, of this group in the morphospace. Another way that's completely equivalent to that one, but that might tell us some other story, is to basically just use an arbitrary point in the morphospace. So here I use the origin of my ordination, and same, you just measure Euclidean distances between each species and the point. Again, that can be done in any number of dimensions you want. And you have here another distribution of all these distances. That will be more disparity as a proxy of the position of the species in this morphospace. So yeah, basically I'll show you an example after by using both how you want to see, you might be interested in the volume of your species in the morphospace and how, if they shift somewhere in the morphospace again. So again, just illustrating, I'm actually not doing any analyses on these guys yet, but we want to see the difference in disparity between these 2 groups. So we can, again, measure, for example, the distances from the centroid, and in this case, again, it's completely made of data, but we might imagine that they occupy the same volume in the morphospace, which is actually misleading, because we can clearly see that our 2 groups are in different places in the morphospace, but they have the same size. So another way to do it is to add this other metric where you can have their position in the morphospace, and maybe we can observe another distribution. So also the nice idea of just having disparity as these distributions is that is actually fairly trivial to do some statistical testing on distributions. Another aspect of all that is if we want to see differences between groups, we might be interested in looking at these differences between groups through time. So that's these like disparity through time, classic papers by Foot and everything. So yeah, going back to this matrix that corresponds to our ordinated space, we can basically, we might be interested to just look at the dinosaur, for example, in the past, and in the present, the bird. So for that, I'm going to propose a kind of novel method that, again, is more arms waving than anything yet. But yeah, so from this matrix, you can also obviously build your phylogenetic tree. Actually, you can also compute ancestral stage reconstruction, so you can basically have the estimation of the morphology at the nodes, and basically that creates basically bigger matrix with your living species, your fossil species, and your putative ancestors. Again, as you can see in this example, I put a lot of missing data. That's not especially a big problem, because sometimes we don't have a lot of confidence in our reconstruction, so we might be conservative or not, depending on user's choice. And so yeah, this kind of using this tree and this matrix with the new data, I propose a kind of new time slicing method, where basically once you have your tree, you can decide just to slice through your tree to have basically an instant snapshot of diversity at the time where you slice it. For example, here, if you slice at the present, where you're looking at the disparity of your living species, then here you can slice like in the middle of the tree, for example, where you have the disparity for these 2 theropod dinosaurs there. But then you might have a problem where you slice along branches, and So one way to, so the problem is which states to use, which species to use for measuring the disparity. So either the ancestor, either the kiwi over there. So basically, again, it suggests that everything is possible, and you can use either models of evolution, for example, Actran or Deltran models. So for example, or you can decide that like evolution is punctuated. So for example, your states don't change and then suddenly jump, or gradual, that like the closer you are to a node, the more likely you will be to have the states at the node, etc. And yeah, so for example, in this model, I just choose the gradual model, and you can do another slice, for example, here, where you have you can slice through different branches and different nodes, etc. And yes, by that, then you just have this series of basically instant snapshots of the morpho space through time, and then it becomes kind of more classic analysis where you have your time on your y-axis and disparity, again, whatever you deem useful in like your problem to measure disparity, for example, the distance from the center is, or the distance from the center, and you can basically draw your scores of disparity at each time being. So again, you have to imagine these points that are more a distribution than points, but maybe distributions seen from above, so with some confidence interval, etc. You can then interpolate your disparity between your time points and add some confidence intervals on that to have results. And yeah, so again, as you might have noticed, I don't have any results yet or anything, but basically all this is a package that I'm developing on GitHub on CRAN. I'm actually doing some things on mammal data sets, but the results are like, the package is not functional yet. But yeah, if you're interested in using these methods, I highly recommend you to have a look at the package or chat to me, because I'm really interested to have users' input for developing this package. Thank you.